Hello, this is Scott Dahman of PowerWorld Corporation. In this section, we will introduce PowerWorld Simulator's Optimal Power Flow tool and go through a few examples on some small power system cases. And we'll start with some simple examples that will help provide some background on what exactly is optimized in the optimal power flow, and look at the implementation and see how the software works and how it determines prices and things like that. Some examples. After we look at just simple LMP calculations, we'll talk about how the LMPs then can be split into different components, which are used in some markets, components of energy losses and congestion. And then we'll look at some visualization stuff. Tomorrow we'll also do some more examples with larger systems. To introduce the optimal power flow, we'll use primarily 2, 3, and 7 bus cases because it's easy to see what's happening. It's easy to see transmission constraints and how they get resolved and things like that on a smaller network. So optimal power flow, anytime you have an optimization, it's usually seeking a best solution. So in the case of power system operation, best is usually considered the point where the operating costs are minimized. So the total cost of meeting the load is minimized and also subject to constraints that are imposed by the transmission system. With the software itself, you can configure it to ignore the transmission system or to consider the transmission system. And in considering it, you can ignore certain limits if you want, either through the limit monitoring settings or through various OPF settings. You can tell it to ignore certain classes of constraints, like all interfaces or all transmission lines, and you can also do it on an area by area basis. So and we'll look at initially where we'll ignore the transmission system. So we're basically using the OPF algorithm to solve an economic dispatch in that context. So again, as we talked in the last section, an ideal power market, or one without transmission constraints, is kind of like a lake or a cloud where you've got generators dumping power in and loads taking power out. And if there's no transmission constraint, then you have a single marginal cost and a single clearing price that's based on the only constraint being that supply equals demand. So the demand is satisfied with the least cost unit up until the point where that least cost unit hits a limit, and then the next least cost unit is dispatched, and so on until you have the demand that's required by the loads, and then that clearing price is considered the marginal cost, and it's the same everywhere if we don't have transmission constraints. So this graphically represents a 2-bus example. There's no transmission constraint. This pie chart represents the loading here, and there's a total of 600 megawatts of load, 600 megawatts of generation, and the same price occurs everywhere. So I'll open that up a little bit later. Yeah, so in the 2-bus case, you can have 2 generator curves right here, and then the dispatch occurs where the marginal costs are equal and where the sum of the 2 outputs is equal to the load. And this concept could also be applied to a much larger system, the only difference being that you end up with more little points and little steps on the supply curve. And if the demand is considered inelastic and we're ignoring transmission constraints, then it can be represented by a vertical line, and the clearing quantity and price is determined by the intersection of that supply curve and the vertical line for the demand. So in real power markets, of course, there can be transmission constraints. There can also be constraints, zonal constraints, where total demand in a zone or a region must equal the supply in that region. And anytime you have transmission constraints, then the marginal cost can become localized and you get different nodal prices at different nodes. So again, in the optimal power flow problem, we're going to minimize a cost function, taking into account the constraints that impact the system. And constraints can be described as either equality or inequality constraints. Examples of equality constraints are the bus real and reactive power balance. So all the megawatts and megavars that are going into a bus, either from transmission lines, generators, loads, have to equal the outflows into that bus. So generator voltage set points, this isn't really impacted, this isn't really optimized, but it's a constraint that has to be met on the power flow side of the optimal power flow. So the generators are regulating a bus, either a terminal bus or a remote bus, to a certain voltage, so that's considered an equality constraint. The megawatt interchange, the exports or imports from an area, that can be an equality or an inequality constraint, as we'll see later. But typically those are considered as fixed amount, so it's an equality constraint. And transmission limits and interface limits, these are typically considered inequality constraints, but they can be modeled in the software as equality constraints, where you can set the software up to tell it you want a certain flow on a line, transformer, or interface. But typically those are inequality constraints, meaning you have a maximum value that a transmission element can support, and it's allowed to carry less than that or up to the limit, but not more. So again, that's more typically treated as an inequality constraint. Generator megawatt limits, minimum and maximum capability of the generator are typically inequality constraints, so the generator can operate anywhere between its minimum and maximum. Reactive power capability curves can be used. Those aren't really optimized again, but they're part of the power flow side. And bus voltage magnitudes, they can be controlled, but they're not really optimized either. So controls that are available to the OPF, most commonly the generator outputs are adjusted. That's generally going to be the case anytime you run an OPF, and then optionally you might include some of these other controls too, like demand response. You can have phase shifting transformers be adjusted to an optimal megawatt level, and transactions as well. Those can be treated as controls. So PowerWorld Simulator uses a linear program in order to do the optimization, and we'll look at a lot of characteristics of that as well going forward. There's also in academic literature discussions of using Newton's method. This is not usually implemented in commercial software because it's slow in determining which constraints really matter. As we'll see when we look at the at linear programming and how the software actually solves it, there could potentially be thousands and thousands of constraints. You know, every transmission line could be something that could be loaded, but practically speaking, there's usually just a handful of elements that end up being congested or run to their limits, and the linear programming software is good at ignoring the ones that aren't needed. So, and then determining how to change the dispatch of generation in order to balance and meet the constraints that really do matter. So linear programming algorithm is very efficient at doing that, which is kind of key. And in a power system, like I said, you typically, most of the limits don't matter. It's just a handful of them that do matter, so you don't need to plug them all in to an algorithm like the Newton's method. So as we'll see too, when we do solutions in PowerWorld Simulator, it iterates between actually doing the power flow, which is the stuff that we looked at in the introductory course as far as solving a system of nonlinear equations for power balance, making sure generators are within their reactive power limits, that's in the voltage control loop, and things like that. So that's done in the power flow solution, and then the linear program basically determines how to adjust controls like generator outputs in order to minimize cost without violating any constraints. And it does that by incorporating linear sensitivities, like PTDF and generator shift factors, for example, so that it understands the impact of moving a generator to a different output and what that does to transmission lines that might be exceeding their limits in order to bring those back into their limits. So the problem is also formulated if you have overloads in your initial system that you're trying to clear with the optimal power flow, then the problem is formulated to give a solution that's valid or feasible through the use of slack variables or dummy variables. So if you have an overloaded line, there's a variable that's introduced into the linear program that has a very high marginal cost associated with it. And because the optimization is trying to reduce the cost, it's going to adjust the controls in order to run that cost down to zero, basically bring the line within its limit, because adjusting the generation, the marginal cost or the penalty costs are set high enough that adjusting generation is a less expensive option than overloading the lines. So that's done through the use of these slack variables or dummy variables to enforce the constraints. Okay, so now we'll move over to PowerWorld Simulator and look at this 2-bus example right here, which in the absence of congestion ends up just being an economic dispatch with a single marginal cost everywhere. Okay, so in PowerWorld Simulator, I'll go to File, Open Case, and inside my training cases, I'll choose the B2 OPF. So there's just a single control area in this case too, as I'll see if I open the Model Explorer right here and I go to the Areas tab. There's just one area, it's called the Home area, and it's on Optimal Power Flow Control. So if I go then to my Add-ons ribbon and click the button that says Primal LP, that stands for Linear Program, it will perform the solution, and then we can see that the generation is set where it's meeting the load. There's a 300 megawatt load at either bus and a generator at either bus, and they're dispatched at different levels because they have different cost structures. And if I look, I can right click here and go to, let's see, okay, so if I right click on a generator, I can look at some of these curves that we looked at yesterday, and the all area generator incremental cost curve shows the there's different cost structures and different minimum and maximum outputs associated with either generator, and it's dispatched at a point where the sum of the output where the clearing price intersects the incremental cost curves, the sum of the output down here equals the load, and the the incremental price is the same at both, or the marginal price is the same. So the clearing price is shown here. It doesn't deviate. And what we'll see too is that under this circumstance, if we did an economic dispatch of the generation using the economic dispatch tool in PowerWorld Simulator, if I change the AGC status to economic dispatch and then just solve the power flow, then we basically get the same dispatch and the same prices. So it does the same thing. If I switch it back to the optimal power flow here, and I'll hit the play button to play the simulation up here on the tools. Oh, actually what I need to do, let me stop that. It's not set up to do the optimal power flow if I do that. What I can do is I can, for example, increase the load, let's say at bus A. We'll make it, say, 400 megawatts. And then if I do an optimal power flow, we have the transmission line becomes congested and the prices are different. So if we go back to that set of incremental cost curves, now we don't, the equal lambda criteria cannot be met because of the transmission congestion. And so extra power has to be supplied from this local generator, and then there's a deviation of the prices. And we'll take a look at that next with a slightly more complicated example, slightly more complicated network with multiple transmission lines. But on a small scale, this is basically what you end up seeing in power systems when you do have congestion. You end up with a constraint, and you end up with, if there is a constraint, you end up usually with higher prices on the receiving end of that constraint than on the sending end. If the prices were, if this generation was less expensive, then you would never have the transmission congestion in the first place. So it arises because we're trying to get as much power as we can from this generator right here. Okay, so that's the 2-bus example. And yeah, when we have a constraint, then the marginal costs can diverge. Okay, so next we'll look at, like I said, a slightly more complicated example. And we'll look at it initially with ignoring transmission constraints and then looking at the impact of adding the transmission constraints. So we'll go to File, Open Case in Simulator, and then choose B3 LP. And we don't need to save the existing. Okay, so a few characteristics about this system. There's 3 generators, one at bus 1, one at bus 2, and one at bus 3. There's a single load that's in service that has 180 megawatts of load. The cost structure is such that bus 1, the generator at bus 1 has a price. If I go open its dialog right here and go to the cost tab, it has a linear term in the cubic input-output model of 10 megabtus per hour and a fuel cost of 1. And then the nonlinear terms are all 0 or approximately 0. So essentially what this ends up being is a cost of $10 per megawatt hour for its output at generator 1, at bus 1. At bus 2, there's a generator that has an associated cost of $12 per megawatt hour. And at bus 3, there's a generator that has an associated cost of $20 per megawatt hour. So going back to generator 1 and looking at its output characteristics, it's got a capacity of 400 megawatts and no minimum megawatt output. So as long as the load is less than 400 megawatts, and if we ignore transmission constraints, then it'll be dispatched such that it's going to get all the power from the least expensive generator. And another characteristic of the transmission network is that all three of these lines are lossless, and they have the same impedance as well. So if there's power generated at bus 1 and consumed at bus 3, 2/3 of the power is going to take the direct route between bus 1 and bus 3, and 1/3 of it is going to go around this way because there's 2 transmission lines in this path and they all have the same impedance. So basically you have twice the impedance in this path as you do in this path if you're looking at power that's injected here and withdrawn here. So to solve the optimal power flow without transmission constraints, the way this is formulated is on the add-ons ribbon, you can open a dialog under this OPF options and results button here. And on this dialog, there's a set of options, common options, constraint, and control options. And if we look at the constraint options, we can see here that there's a checkbox which applies globally to all transmission lines in the system where we're disabling the enforcement of the MVA limits. So also from this dialog you can click this Solve LP OPF button, which does the same thing as clicking the Primal LP directly from here. But since we have the dialog open, we can just click that right now and then click OK to close it. And now we see we have, there's some fields associated with each of these buses which shows the megawatt marginal cost, or the LMP, at the bus. So because we're ignoring the transmission constraints, we're not enforcing this, we're getting all the power from the generator that costs $10 per megawatt hour, and the LMP at every node in the system is the same. So you can think of the LMP, or the megawatt marginal cost, as what would the change in cost be to get 1 more megawatt delivered to that bus. And again, if we ignore the transmission constraints, the cost of delivering 1 megawatt to any bus is $10 because you would just get 1 more megawatt from this generator, as long as it's not at a limit, which it's not. So okay, so if we want to enforce the limits, we can just go back into that dialog and disable that checkbox and solve that. So let's go ahead and do that so we can see what happens if the limits are enforced. So from the add-ons ribbon, I go back into the OPF option results. I go to the constraint options and I clear the checkbox that tells it to disable line and transformer MVA limit enforcement. And then I can click Solve LP OPF and then OK to close the dialog. Now what we see is the load's still the same at 180 megawatts, but the generation dispatched has changed. So instead of getting all of the power from the least expensive generator, we're now only getting 120 megawatts from the generator at bus 1, and we're getting 60 megawatts from the generator at bus 2. And then we also have different locational marginal prices at each bus. Those have diverged. So we still, at bus 1, we still have $10 per megawatt hour because the least expensive way to get 1 more load delivered here would be to supply it locally. because in doing so, you don't impact the transmission network at all. Same thing happens at bus 2. We don't have any load here yet either, but if we wanted 1 more megawatt of load at bus 2, it could be supplied locally for $12 per megawatt hour by this generator, and that would also not impact the transmission network. At bus 3, we have a cost of $14 per megawatt hour, which isn't directly related to the cost associated with any of the generators. Remember, we had $10 cost associated with this generator, $12 with this one, and $20 with this one. But this generator is still not operating. We're still getting power from these. And we have we have a limit, transmission limit met here on this line at 100%, but we don't have a limit on this line. So we could still get power in, but the cost is $14 per hour, and we'll take a look at exactly where that comes from. So again, here's a summary. Like I mentioned, the network has the same, all the transmission lines have the same impedance. They also each have the same limit of 100 MVA. And the real power losses in the transmission network are 0. It's just the reactance that has a non-zero value. This is the cost structure for the 3 generators, and the load is only at bus 3. So we might also want to check, it was actually saved in the case already, but as we did in the 2-bus case, we might also want to make sure that the area is set to OPF control, which it is in here. And of course, you can do that by looking at the Model Explorer and making sure the AGC field for the area in the case is set to OPF. And we initially disabled the enforcement, and then this is what we saw. So we'll take a look at linear programming a little bit in the next section, but the way it's formulated is there's an area constraint that must be met, and there's a transmission constraint that must be met. If we ignore the transmission constraint, we just simply get the area constraints, and this is a variable associated with the output, the power output of generator 1, generator 2, and generator 3 respectively. And there's a sensitivity of 1 with respect to just meeting the power balance in the area, meaning if you need 1 more megawatt anywhere in the area, you can get 1 more megawatt out of any of the generators. The sensitivities are all the same. If we include the transmission constraint, we insert another line into the formulation where we have sensitivities or generator shift factors for each of the transmission lines, and they're either 2/3 or 1/3 depending on where the power is coming from. So that gets enforced as well. We'll take a look at in more detail in the next section about that. But anyway, this is the solution that we get that we just saw when we enforce the transmission constraint, and the marginal cost is set by the different generators. Now at bus 3, the marginal cost is actually, the reason why it's 14 is because it's actually composite of two marginal units in the system, the one at bus 1 and the one at bus 2. The least expensive way to get 1 more megawatt to the generator, or to the load rather, at bus 3 is to increase the output of the generator at bus 2 by 2 megawatts and to decrease the output of the generator at bus 1 by 1 megawatt. In so doing, we keep the flow balanced on this transmission line, and extra flow just ends up showing up on this one because the 2 megawatts here cancels out, the flow from 1 megawatt here. So this line stays balanced at its limit, and the 2 times 12 minus 10 is where the 14 comes from. And we could verify this too in simulator if we use difference flows, like we did in some of the examples in the intro course. We can go to the Tools ribbon, go to the difference flow tool, and set the present case as the base case. And then we can make an adjustment to this load by increasing it by 1 megawatt. And I'm just going to open the dialog to do that because these controls here I think will adjust it up and down by 5 or 10 megawatts. So I'll come into the load dialog and just change the constant power load to 181 megawatts. And then click OK. And then if I go to the add-ons ribbon and click the Primal LP again to resolve, it'll redispatch the generation. And if we go to the difference flows, we can see what happened is we got 1 extra megawatt here that was supplied by 2 extra megawatts here and 1 less megawatt here. And so the change in flow on this line is 0. The other 2 lines each carry 1 more megawatt, but they're not at their limits. So that can be done without any issues. So we could see what happens if I switch back to the present case. If I increase this even more, let's say click the pinwheel button, and that'll jump it by 10 megawatts to 191. If I solve the Primal LP again, this transmission line gets loaded up even a little bit more, but we still haven't hit a limit on it. It's still the same. If I increase it again, solve it again, now we've, with 200 megawatts of load here, we've exceeded the capacity of 100 megawatts on each transmission line coming in from the rest of the system, and incremental power now has to be supplied locally. So in that condition, then the locational marginal price for this bus then jumps to 20. Which, and again, this is kind of the same thing that you see in larger systems, just on a larger scale with more transmission lines in the network. But when capacity on transmission lines is met or exceeded, then generation has to be redispatched in a way that causes the prices to diverge in different parts of the network. We could have another condition where, let's say this generation isn't even available, it's offline. So now we have a situation where we've got more load at this bus than we have transmission capacity to supply it. So that's that can be termed as a load pocket, where you've got a part of the system with not enough generation capacity in it. Now if we solve the linear program, we end up with what's called an unenforceable constraint. If we assume that the load is fixed and cannot be curtailed, we don't have enough capacity to on the transmission network, so at least one of these transmission lines will end up being overloaded. And then there's the LMP is then derived from essentially a penalty cost. It's not derived just from the generation alone, but from the fact that there's a slack variable, as we mentioned earlier, that's put into the linear programming formulation that cannot be removed. The constraint can't be satisfied, so the slack variable stays in the linear programming basis, and it influences the solution. So, and that's driven, the penalty cost, you can adjust it if you want. If you go to add-ons, OPF, options and results, there is if you go back to the constraint options, there's a variable here called the maximum violation cost in dollars per megawatt hour, and that's set to 1,000. So there's a component of that in the 1,023. The marginal cost of violating, that limit is $1,000 per megawatt hour. So that's what drives that. And again, you can change it. It's really just important that it's sufficiently high that the software is going to try to meet the constraints by moving the other controls, by moving generation, if load is available as a resource, adjusting load, and so on in order to get the costs down. But if there are no controls available, then the limits are violated and it's considered an unenforceable constraint. Okay, so this slide just recaps what we did on the example where we had generators at bus 1 and 2 operating, and the load such that both lines were not overloaded or both lines were not congested. And yeah, the impedance dictates that if the generator at bus 1 supplies all the power, then 2/3 of it takes the direct path and 1/3 of it loops around. And it's kind of the opposite case if we're looking at power that's injected from bus 2 and withdrawn at bus 3. So yeah, and if we look at the sensitivity, so we basically have two constraints in the linear program formulation. To get 1 more megawatt to bus 3, we need the total change in generation has to equal 1 megawatt. Again, it's a lossless system. So the output from generator 1 and the change in output from generator 2 has to equal 1 megawatt. And then in order to keep the flow balanced on the line from 1 to 3, looking at the sensitivities or the shift factors for those two generators, we get 2/3 of the output times the change in output from generator 1 plus 1/3 of the same from generator 2 has to equal 0. So you end up, to satisfy these two equations, you end up with increasing the output of generator 2 by 2 megawatts and then -1 for this. And then both of those equations are satisfied, and then the resulting change in cost is the 14. So, and then you can also look at the marginal cost of enforcing constraints, and this is, in markets, this is sometimes called shadow price as well. So we could look at, for example, what happens if we change the limit on this line. And I'll go back to my difference flow tool again and set this present case as the base case, and then make an adjustment here on this transmission line of the limit. So we'll change it from 100 to 101 MVA and click OK, and then resolve the optimal power flow. So now we can see when it's resolved, it redispatched the generators such that it pushed this right back up to its limit, and now it's carrying 101. And if I look at how that changed things on the difference case, I can see that this generator was able to increase, the cheaper generator was able to increase by 3 megawatts. And the more expensive generator dropped by 3 megawatts in order to keep the load balanced. And that resulted in a decrease in cost of $6. So the savings is $6. Or another way you can look at it is the cost of enforcing that constraint is $6 per hour, and that's the shadow price, or $6 per megawatt hour on the constraint. And there's a way you can look at those as well in Simulator. I'll go back to my present case, and then if I go into the Model Explorer, there's actually a couple places you can look at this, but there's one display that's dedicated to looking at constraints. In the Model Explorer, if I go into the Optimal Power Flow group, and then I choose Branches, then there's a list of constraints here. And then the shadow price is this MVA marginal cost column right here. So if you mouse over that, it explains that it's the cost of enforcing the limit. It can be interpreted as how much the system would save by increasing the limit by 1. So And it's shown also in the table that this is a binding constraint, and it has an associated cost of $6. So, and again, if we go back to that point where the load is above 200 megawatts and the generator at bus 3 is offline, and as we mentioned, that results in an unenforceable constraint. And that table in the Model Explorer will now list the line from 1 to 2 as being unenforceable with a shadow price of 1,000, and then the other one becomes a binding constraint as well. So again, those are artificial, derived from the penalty cost, but you would see the total cost change still if you increased or decreased the limit on either one of those lines. It would redispatch the generation, but at least one of the lines would still be overloaded as long as you didn't have enough capacity to serve the load. Okay, so this slide just recaps how you can look at the table of constraint costs. And then this just shows, again, algebraically in the formulation of the problem, if we're just changing the limit, the total change in output, the load doesn't change again, so the total change in output has to equal 0. And the sensitivity equation can be set equal to 1 because we're allowing 1 more megawatt to flow there. And then we can solve that equation such that the more expensive generator can drop by 3 megawatts and the other one can increase, which saves $6. In this one, the generator is available, so it can be supplied locally, but no more power can be imported from the other buses. In this case, if the generator is offline, then you have the unenforceable constraint. So looking at unenforceable constraints, the question then becomes, is it a valid solution? Well, it's really just an arbitrary solution. And like I mentioned earlier, if you have unenforceable constraints, that means that the slack variable or the dummy variable associated with that constraint cannot be removed, even though it has a very high cost associated with it. We can't find a lower cost solution because the load in this case is fixed. So, and then you can adjust that with that variable in the dialog. Okay, so we'll continue with just the explanation of some more of the things that are on that constraint options dialog. So we looked at that earlier on the, and this is on the add-ons ribbon, OPF options and results. And if you go to the constraint options, we looked at earlier, you can disable line and transformer MVA enforcement. And we also looked at the penalty cost or the maximum violation cost that's applied to unenforceable constraints. You can adjust those numbers if you want. I don't normally make adjustments to any of these, but there's also a couple other variables too. The percent correction tolerance just gives rise to like a deadband for constraints. Normally you just don't need to change that at all. The auto release percentage has to do with, again, in the formulation, in the tableau, it releases constraints from the basis if they no longer become binding. So there's this process of, as we mentioned earlier, going between the linear program, which does the control adjustments, and then those adjustments are passed over to the actual power flow program for it to solve the system of nonlinear equations for the power flow and the power balance. And there's an iteration when the controls are passed over and the power flow is solved. It's possible that new violations could come up that then need to be resolved through another adjustment of controls. So throughout the iteration process, constraints can become binding, and under a new future dispatch, they can back off of their limits and become not binding anymore. And so this is just saying that if a line gets down to 75% loading, then it's just going to remove it from the basis. And another thing we mentioned earlier is that the linear program is fairly efficient for power flow problems, because typically you have lots of transmission lines in a power system, but only a handful of them actually matter in terms of the limits and being binding or unenforceable. So, when a control is released, it's just removed from the basis. So, again, those variables are things you normally just don't even need to adjust, but they're there if you need to. And there's a similar set of variables for interfaces, and then similar ones for phase shifting transformers too. You can ignore those. I don't normally make any adjustments to those variables, but if you need to, they're there as well. But you could probably just leave the defaults for most practical applications. Okay, so, and as we mentioned earlier, that the violation cost is high because simulator is going to try. The linear program is going to want to reduce costs as much as possible, so it'll move controls before it'll allow a transmission line overload to occur. But if there's a load pocket and an unenforceable constraint, then that's going to remain in the solution. So having those in there can be helpful because it tells you, where the load pockets are, and you can make some adjustments if needed, or just leave it in there as well. So it could point you to some bad data, or just some conditions that are unrealistic. Maybe the load's too high. Or it could just be a situation that should remain in there. And we'll look at some of those examples of, unenforceable constraints that can be caused by different things and what you might need to do to make adjustments. A lot of them are also caused by reactive power flows, and if you're primarily using the DC power flow, then it's not so much of an issue. All right, so graphically, this is what the maximum violation cost looks like, and like we mentioned, you can, it's a constant on the dialog, and it just gives rise to a slope. So you can think of a transmission limit as having a function where if the transmission is operating anywhere below its limit, there's no cost associated with it whatsoever. When it hits its limit and it goes up, then it starts increasing cost at a rate of whatever that value is. By default, it's $1,000 per MVA hour, and that's what gets applied into the cost function. So the more heavily loaded a line is, the higher the cost in dollars per hour. So simulator is going to try to drive that back down if possible to the limit, as close as it can. So if you want to, you can also model a piecewise linear limit cost. So instead of having just one cost associated with violating a limit, it can be have different breakpoints, and this is done with the limit group in the limit monitoring settings. We looked at that, I mentioned I think that the tab was there when we looked at limit monitoring settings yesterday, but outside the OPF it doesn't really have any use, so we'll take a look at it here. And instead of what you can do then, instead of having a single slope that ramps up from 0 to some value at the limit, is you can have it be such that small overloads have small costs associated with them, and larger overloads have larger costs associated with them. So I guess the advantage of doing this might be if you want to consider a situation where having several lines overloaded by a small amount should be preferred to having a single transmission line that's really overloaded, then this type of penalty function would encourage that type of solution because it costs less in the penalty function to have a line overloaded at smaller values if you put smaller slopes in like this. So we could do this just going back to the 3-bus case. Close this, and I'll go to my tools ribbon and then my limit monitoring settings, and we just have the single default limit group here. And what we can do is we can right click on that and choose to show its dialog, and then right here you can have a limit cost, a piecewise limit cost, linear limit cost associated with it. And if you check that box, then you get this, and it defaults to what the behavior is in the OPF constraint options, where you have a penalty that starts at $100 or 100% at $1,000 per megawatt or MVA hour. In the case of transmission lines, it's megawatt hour for interfaces. So if we wanted to add points to that, we could just click in there and hit the enter button, and then we can put in a breakpoint. So let's say we could put in a breakpoint at a 5% overload or 105% of the rating. And let's say for 100, we just have a small penalty of say $10 per megawatt hour. Once we get to 5%, let's say we have a penalty of $100 per megawatt hour, and then if we're 10% overloaded, we'll then ramp it up to 1,000. So if we use that for any elements that belong to that limit group, then this setting would override what's in the OPF constraint option. And I can click OK, and then come back here. Now let's ramp up this load to say 211 megawatts. Now if I solve the OPF, what I see, instead of having all of the overload appear on one transmission line and some of it, or the other one being a binding limit, they're both exceeding their limits. This one is settled at a breakpoint, at the 5% breakpoint, and then the rest of it comes here. And the penalty cost is lower, and the LMP at that bus is lower. So you can see that. And then the different values would be reflected. If we go to our Model Explorer, go back to the Model Explorer, and we look at the list of binding and unenforceable constraints, we see that we have a lower limit cost associated with them as well. And of course, if we increase the load even more, then we get to the point where we're kind of back up to the $1,000 range because we've exceeded, although this one's settling at a breakpoint. So it's got a, it's still trying to minimize the total cost, and that total cost is then, computed from the piecewise linear curves instead of from a single slope penalty function like the default option is. Okay, so again, this just shows how you can look at binding and unenforceable constraints in the OPF branches display. And there's also a tab for interfaces and nomogram interfaces if you have those and if you have limits associated with those. Also on the options dialog, there's the first tab we kind of skipped over earlier. It's the common options tab, and this has a choice of objective function. We've looked only at minimizing cost, but if you want, you can also use the OPF tool to do a minimum control change optimization. And what that could be useful for is if you don't have cost curves associated with generators, but you just want to take a case a starting case that may have some overloads in it to begin with, and you want to clear those overloads without perturbing the generation dispatch more than necessary, then you would choose minimum control change for the objective function. And then internally, what the algorithm does is it assigns the same cost to adjusting a control regardless of what direction it increases or decreases it, whether it increases or decreases the output, for example. So again, it's going to try to resolve all of any constraints that are violating with a minimum movement of controls, typically generation, but it can be any other control too. If you're using the reserve modeling tool, which we don't cover in detail in the training, but the slides are included, then you would check the box for including the OPF reserve requirements, and then that would also necessitate more data as far as populating reserve requirements and reserve bids from resources like generation and load. You can also globally disable or enable entire classes of controls. At this point, I'll just go ahead and shift over to simulator and then go back into that dialog so that we can see it there in the options and results and the common options page. So we have the control function. So here, if we want to use load controls for demand response, and again, we'll do an example of that tomorrow, we would decheck this box, and then we'd also have to go in and enable individual loads and put we have to put benefit curves in for those loads as well. So different classes of controls can be enabled or disabled here, and these are global settings. There's also area level settings, which we'll take a look at in a moment for a lot of these controls. So you can enable or disable them there. And then on the device level, of course, you can make things AG-seeable and so on. So the things on the right, you generally don't need to adjust these from the defaults in most cases, but there's a number of iterations that's in the linear program that doesn't have to do with the actual power flow solution, but rather with the adjustment of controls in order to meet the objective function at either least cost or minimum control change. So you can normally just leave those set to where they are. I think there does need to be some cost associated with phase shifter movement in order to keep them from moving too much, but usually you keep that really low or close to zero, and so forth. And the other stuff, there's some check boxes that you can optionally check or decheck as needed. So, and then some of these options are described in greater detail on the slides as well, as far as the objective function, the control variables, iterations, and cost of moving, phase shifters, and there's also for distributed fax devices, which are not commonly modeled, but you can also have those as OPF controls and costs associated with movement of those. Okay, so control options is the next page over, and we'll take a look in greater detail at some of these options later, but for now we're just pretty much going to leave them at their defaults. There is a feature again that we'll take a look at a little bit in some of the examples tomorrow as far as fast start generators. Strictly speaking, simulator does not have a unit commitment algorithm. So in other words, the controls that are available to the OPF normally are going to be just the controls, just the generators, for example, that are online and that are AG-seeable. So if not, then the output remains fixed or the generator remains offline and it's not able to be used. You can designate certain units at the generator level as being fast start units, which will allow simulator to commit them or turn them on if they help reduce the cost. But again, it's not a strict optimization. It's not a unit commitment. It does not incorporate temporal constraints like ramp rates or minimum uptime or minimum downtime. There's no notion of time really in simulator. So it simply just says that if you've got a fast start unit and you can reduce cost by turning that unit on and dispatching it, then it would allow simulator to do that. So there's a global enabling of that, and then at the device level, you also have to do stuff. And then you can also have a decommit unit. So if there's an expensive unit where the cost would be reduced if you just turned it off altogether, then it can do that if you check that box and you make the unit fast start. So I could do a quick example here in the 3-bus case. So this unit's offline right now, and we've got overloads. If we made this unit a fast start unit, then again, simulator could commit it. So if I right click on the unit and open up its dialog and then go to the OPF tab, I can designate it as a fast start generator, which again would just make it available to turn it on if that would reduce the cost. And if I click OK, then also I need to make sure that it's enabled globally in the OPF options and results on the control options. I have to make sure that this is checked. So, and there's a separate option for allowing commitment and decommitment. And the reason why we do that is sometimes decommitment can be dangerous, especially if you're using the AC power flow. If a unit's decommitted, it cannot provide reactive power at all. If it's committed, it could still be back down to its minimum if it's really expensive and not needed, but it could still be providing megavars. So it could cause some instability in the power flow solution because the linear program doesn't, understand the nonlinear relationship between megavars and voltages. So as it's iterating, it could cause the power flow to fail. But if you're using the DC power flow, or if you're in a situation where you know that the units that you've designated as fast start units aren't going to cause any problems if they're taken offline, then you could check that box as well. So if I click OK here and then click the Primal LP, what I see now is that simulator turned that unit on and dispatched it at a certain level. Now, because I have my piecewise linear curves, it actually determined that it's cheaper to overload this line up to 5% of its limit and only dispatch this up to a certain level. But having that fast start designation in there then allows simulator to commit that unit. There's another variable in there associated with fast start units that says round to on percentage of min limit. And what that means is that with a fast start unit, if it has a minimum output that's not 0, then there's really a discontinuity in there between not committing the unit and committing the unit. If the unit's taken offline, then its output is 0. And if it has a non-zero minimum and it's put online, then there's a discontinuity in there that the linear program can't directly handle. The linear program needs to have a continuous range between the minimum and the maximum. So if you, for example, you have a unit that has a minimum output of 100 megawatts, then what it does, what simulator is going to do with that is it's actually going to run 2 iterations, consecutive iterations of the linear program, where first it's going to assume that the unit has a minimum of 0, because then that provides a continuity with the unit being disconnected. If it determines that the optimal output of that unit is above the percentage that you put in here of the minimum, then what it'll do is it'll turn the unit on and set it to its minimum, just kind of heuristically. and then solve the power flow, and then, make adjustments if needed. But, in the example of a unit that has a minimum of 100, if on the first pass it determines that the optimal output of that unit would be 50 megawatts, as long as 50 exceeds the value in here as a percentage of the minimum, then it would turn the unit on and set it to 100, the minimum for the unit. If it determines, that the optimal level would be, say, 1 megawatt, it just wouldn't even bother turning it on. So that's how that's used. And you can adjust that if you want. It's 2% by default, but you could change it to, whatever you want. It's biased so that it's not going to decommit units unless they need to be at a low value. But if you wanted to, you could put in 50% if you wanted kind of a more balanced approach. But again, the default is biased towards committing units and away from decommitting units. So that's why it's a low value in there. Other options in here, you don't normally need to mess with these, especially the ones on the right. Normally when you go to solve the optimal power flow, simulator is going to do an initial solution to make sure that the power flow is converged. And normally you want that initial solution to happen with participation factor control, because that's the method out of the 4 choices that results in the least disruption of individual units. And then, so that's during the initial solution. And then also, if you have areas on optimal power flow control, but you just go to do the single solution for the power flow, it's not going to do an optimal power flow then. It'll put the areas on whatever type of control you select over here. And again, participation factor control is the default and the recommended option, because that usually results in the least amount of disruption to your operating point, which normally you want set through the optimal power flow when you do that. In the lower left here, it talks about if you have cubic cost curves, then how does it handle the conversion of those to linear cost models? Because the OPF has to internally use linear cost models. You can still have cubic cost models, but it has to do an internal conversion, and normally it does a curve fit based on the number of points per curve. And the default is 5. You can change that. If you want to make it more granular, you could increase that. I think there's a trade-off between computation speed and maybe numerical stability. Is better with fewer points per curve, but maybe the accuracy of the fit is better with more points per curve. So that's the trade-off. You can optionally choose to convert to specified points per curve or specified number of megawatts in a segment. So then in that scenario, generators that have a larger operating range would have more points than ones that have smaller operating ranges. So you can do that too. Okay, and then some slides that just describe some of those features that we just went through. Okay, and then also on the options page, so each area or super area has an AGC tolerance, and the optimal power flow is going to actually try to get the ACE down to as close to 0 as possible. And so yeah, it's going to try to get them exactly 0. But if you want it to have just a little bit of wiggle room, then you can uncheck that box, and a constraint will be considered enforced as long as the ACE is less than the AGC tolerance. So it kind of treats it then as an inequality constraint. But normally the LP is going to treat the export constraints as equality constraints, and it's pretty good at that. So I don't think you need to change the default, but if you want to, you can. Okay. And then, yeah, as we mentioned earlier, if you're using a cubic cost model for some of the generators, it will internally convert those to linear models. It won't change your data. It won't get rid of your cubic cost models. But that option again just tells it how many points to use or how many megawatts per segment to use. So, and this is just a graphical representation again of that curve fitting that it's going to do internally. Okay, next we'll take a look at a slightly larger case, the 7-bus case, and this will be the last hands-on example of this section. There's a few graphics in the back that show some other cases, and tomorrow we'll even look at some larger scale cases. But with the 7-bus case, it's a multi-area case, and we can look at a few different things. We can look at marginal losses there. We can look at the differences between dispatching the 3 areas individually with fixed export constraints, or having dispatchable transactions between them with a minimum and a maximum limit, or putting them all in a super area, so like an ISO control of multiple areas and how those are different. So yeah, let's open. Go to File, Open Case, and we'll choose B7 flat LP, LP for linear program. Okay, and again, this is a same topology. I think there's a few differences on like generator minimums and loads and stuff like that, but it's generally very similar case to what we've seen in the other 7-bus cases. Same topology. And we have a multi-area case here. So we can go into the Model Explorer and look at the area, the OPF area displays. And another way you can get to that, so you can open the Model Explorer as we did earlier, and then there's a group of displays under the folder called Optimal Power Flow. It's just a matter of personal preference. I usually find myself just going into the Model Explorer because I normally have it open all the time anyway, and then looking under those folders for those displays. But you can also directly get to those displays if you want from the add-ons ribbon. And then there's this drop down under OPF Case Info, and then you can pick any one of those. And what it'll do is it'll just take you to the Model Explorer and open the corresponding tab. So here, on this tab, we see that the 3 different areas in the case, and the AGC status for all of them is set to OPF, so it's ready to go there. We looked earlier at some of the control options that can be set globally in the OPF options and results, and a lot of those features are also can be adjusted at the area level. So for example, whether or not phase shifters are available for OPF control, we're not really going to look at those in this topic, but in a later topic we'll look at those. That's grayed out, and we can see if we mouse over, anytime you mouse over a grayed out thing, it'll tell you why it's grayed out. So it says that the phase shifter controls are disabled in the OPF options. So what that means is that in the OPF dialog globally, there's a checkbox for the control variables that we looked at earlier where phase shifter controls are disabled. So that overrides the settings in the area. If you enabled that, then you could then choose if you want to enable or disable it for certain areas as well. So that's, if it's set to yes, that means it's enabled. So the enforcement of limits for branches and interfaces can also be toggled on or off at an area level. So it's similar to really to limit monitoring as far as the OPF goes, but if you toggle something to no, the limits can still be monitored and reported as a violation, but the optimal power flow won't try to relieve them if they're ignored here. So you can do that for branches and for interfaces. You can have bus angle enforcement, which is not commonly used, but that's an option that you can do in the OPF control. Loads, you can enable load dispatch or demand response on an area basis. Again, that's also disabled globally in this case. So that's set to no. And then other controls here too. The inclusion of marginal losses, I'm going to go ahead and toggle that to yes, because we're going to use an example with those later where we'll want to use the marginal loss sensitivities to resolve the LMP into components. So we can set that to yes for each area that we want that done, and we'll choose all three areas. So anyway, there's that display there, and then there's other displays as well. For generators, again, we mentioned whether or not generators are fast start generators. In the earlier example, I just toggled that on the generator dialog, but there's also, under the OPF grouping, there's a list of generators. And so generally, there's a couple different levels where you can enable a generator for OPF control. Normally, I just use the AGC setting and just, if I want a generator to not be an OPF control, I just take it off of AGC individually. But you can have a generator be AGCable in the power flow and then have it be different for the OPF. Like for example, I could toggle this generator off AGC, and then there's another column called OPF megawatt control. By default, that's set, it has 3 values, and the default is if AGCable. So it's basically saying if the AGC field is toggled to yes, then that generator can be an OPF control. But you can also set that to no, which means that generator will never be an OPF control, even if it's controllable in the power flow, or you can force it to yes. And I find myself just not using this field at all, leaving it all at the default if AGCable, and then just enabling or disabling generator control by toggling the AGC. So what you might want to do, for example, is if you have like base load units, like nuclear units that you don't want the OPF to adjust at all, you can just leave those to not AGCable. Or if you have generation that's not really dispatchable, like wind or solar or hydro in some circumstances may not be dispatchable because the output may be fixed by non-electricity considerations. So you could take the hydro units all off AGC, so you can do that. And then here's the column for the fast start variable. You can optionally toggle those to yes if you want to use generators as fast start. And then this fast start status column will just be populated after you run the OPF if a unit was turned on or off by the algorithm. So, and then if you have super areas, you have some similar fields to what you do with the areas. And we'll take a look at that later in this example as well. Okay, so next we'll take a look at the LMPs and how they can be resolved into components for energy loss and congestion. And so one thing, we already did this step. That's what I did when I was looking at the OPF areas display, is we toggled the include marginal losses column of each area to yes. You might also optionally want to adjust your loss function that we looked at yesterday in the sensitivities. If I go to the tools menu and I go to sensitivities and then loss sensitivities, this is set to do not calculate, but even if it's set to that, the OPF can still calculate them. It just won't be calculated now. But you could choose one of these different loss functions if you want. I normally use the entire electrical island sensitivity there. But like I said, you don't necessarily have to adjust this because it'll still calculate them if the OPF is telling it that it needs it. So I close on that. Okay. And then next we can just go to the add-ons ribbon and then solve the Primal LP. And now we can look, there's a couple different places you can look at the LMP results. In the earlier example, we just looked at it on the one-line diagram. There was a one-line field associated there, but we can also look at them tabularly in either in the results column or there's also an OPF buses display. So these are just, the results are just bus fields. If I go to the buses display, it'll show the megawatt marginal cost here. The various components are not shown by default here, but you can add them here if you want with the display column options. They are shown by default if I go into the OPF dialog, go back there, and then go under results to bus megawatt marginal price details. And so here it has a column for the whole LMP, and then it has columns for the energy, congestion, and loss components. So, and then the slides explain just a little bit how those are calculated. There's a few different options that you have for breaking it out, because really what happens is it calculates the LMP first and then breaks it out into components. It's not like it calculates the components and then adds them up to get the LMP. It's the other way around. So to figure out how to break that out, there's a reference that's applicable for energy and losses. And there's the reference is specified either with the area or with the super area, depending on whether the OPF control is done at the area level or the super area. So here, if we look at an area dialog or a super area dialog, then we'll see these options here. So I'll go back to my Model Explorer and then look at the OPF areas display. And if I right click on an area and choose to show the dialog, and then from there I go to the OPF tab, then down here in the lower left there's the selection for the cost of energy lost in congestion reference, and there's 4 different options. So, and these options are then described in detail on the slides. The default is to use the existing loss sensitivities directly. And so what does that mean? Well, if you use the existing loss sensitivities directly, the cost of energy at every bus in the area or the super area is equal to the cost of enforcing the constraint for the area. So basically, it's the cost of the cheapest unit in the area. So if you're just trying to get, if you're just trying to strictly meet that area constraint without respect to transmission constraints, then the cost of energy will be set to that. You can also make the cost of energy be a weighted average of all of the LMPs in the system. So that's what this equation represents. It's like a sum of, so in the weighting is this alpha sub n divided by 1 minus L sub n. And the L sub n is the loss sensitivity at the bus. The alpha sub n is the weighted factor. And then this is just the marginal cost at the bus. So it's a weighted average of all of the LMPs in the area. And the only thing, the alpha varies depending on if you select these different methods. If you choose the area's buses load option, which is the second one right here, then the alpha is just the load at each bus. So it's good. The energy price for every bus in the area is going to be a weighted average of the LMP at all the buses in the area, where the weighting depends on the load. Of course, divided by 1 minus the loss sensitivity too. So that's in there too. If you use the injection group as a reference, then you pick a specific injection group. If you choose that, you have to pick an injection group that you created, and then it's just going to weight the participation factor of the points. So every point in the injection group is attached to a terminal bus, and then it'll use that participation factor associated with the LMP at that bus. And then you can also pick a specific bus in the area. If you choose that, then you click the Find button and you go find a bus. And then the LMP at that bus would then set the cost of energy for that area. The LMP divided by 1 minus the loss sensitivity at that bus. So, okay, and then the cost of losses is just going to be equal to the opposite, the negative of the loss sensitivity times the energy component that was calculated in the previous step. And then this, it depends on the reference that you pick in the previous one. So if you use the existing loss sensitivity directly, then it's just going to be, use the loss sensitivity for that bus. If you use these different options, then it does some other conversions and some weighted factors in order to get the loss sensitivity. So, and then in each case, the cost of losses is equal to the negative of that times the cost of energy. And then the congestion component is just the leftover piece. So you take the LMP minus the energy minus the losses. So if you pick different references, you can get different values for energy losses and congestion. It wouldn't change the overall LMP though. So that's how that's done. Okay, and then if you want, you can do some examples in that case, changing the loss sensitivity. And we could do that with difference flows real quick too. So we can go in here and go to the tools, difference flows, set the present case as the base case, go into this area and change the reference, say to areas buses loads. Then we can solve the LMP. And then look at the differences. In the OPF dialog, I've got all the components here. You can look at the difference case. The megawatt marginal cost doesn't change, but for area top, the energy, congestion, and losses components change a little bit. So for area left and right, they don't change because I didn't make an adjustment to those references. Okay. So next we can take a look at the effect of using a super area. Super areas can be used in the OPF, for example, to model like an ISO. So you have a group of areas that are dispatched together, and it has the effect of reducing the number of equality constraints for the exports, basically. If in this case we have 3 different areas and we have 3 different export constraints. If I go to my Model Explorer, recall from yesterday, I think this is pretty much a similar setup, but there might be, yeah, there's some exports that are in here. It looks like there's a 50 megawatt export out of area left that's probably going to area top. So if I look under aggregations and areas here, I can see, make this a little bigger. Yeah, I can see the area left is exporting 50 and area top is importing 50. But that's a fixed constraint. I go to solve the OPF and it doesn't change that export at all. I'm still constrained to export 50 megawatts from here to here. And then it can adjust generation within the area. If we create a super area, then it gets rid of those intra-area constraints, and you just have a single power balance constraint for the whole super area. So this export could change. So what we can do is I'll go ahead and set the present case as the base case again in my difference flow tool, and I'll put the super area on OPF control, redispatch, and see how things changed. So you can go over here under aggregations, or actually under optimal power flow. I'll open the super area display. There is a super area, and it's off AGC right now, which means that individual areas are going to be on control, not the super area. But what I could do is I can change this super area's AGC status to OPF. If I want to include marginal losses for this super area, then I can optionally change that to yes. And then there's also, for the super area, if I show the dialog and go to the OPF tab, there's also the same options for cost of energy loss and congestion reference as we had on the area display. So by putting that on OPF control, again, the area constraints then go away. If I go to the area tab, it shows the ACE is grayed out and the AGC status is grayed out because the areas are on super area control. And if I go to the add-ons ribbon and resolve the Primal LP, it redispatches the generation, and now we have non-zero ACEs for the individual ones, but it's grayed out because it's not enforced, it's part of the super area, and the actual exports change too. So now area top is actually exporting, instead of importing 50 megawatts, it's now exporting 150 or 136. Area left is importing and area right is importing. So, and we can see, there's more generation that's at a limit. If I look at my difference flows here, I can see by removing those constraints, for the areas, that it changed the hourly cost. It saved $903 with the new generation dispatch, which is more globally optimal. But in some generators decreased and some increased. But the LMPs don't necessarily go down everywhere. They might go down in some locations, they might go up in others. It's more globally optimal, but it's not necessarily result in higher or lower prices for any particular bus. If I go to my OPF buses display, I can see here the megawatt marginal cost at some buses. Like at bus 6 and 7, it went down. At bus 5, it actually went up. So that's right here. Because it requires a different mix of generation in order to get the marginal units delivered. And this is looking at a contour. So we could apply a color contour as well under the contouring. And with separate areas, we have a pocket, basically a seam. This can be called a seam in markets where you have two markets and you have, or in this case, 3 markets. But there's a kind of an artificial barrier in terms of the export constraint. So in this scenario, because there's only one generator in this area, all of the marginal power has to be supplied from that area in order to keep the area constraint met. And if we put it on a super area control, now this generator can back down and this area can import power from outside. In so doing, we end up hitting limits on some of these lines that have high sensitivity to delivering power to this bus. and the cost drops at this bus, but it increases in other locations as well. Bus 5 is now kind of at the receiving end of two constraints right here. So to get more power to bus 5, you've got to get it from places that tend to unload these constraints, which is not the cheaper generation up here, but the more expensive generation down there. So anyway, we could do similar to what we did in the 3-bus case. We can go in and adjust limits on line constraints to look at, we relax limits and see how that changes things. We can choose to ignore certain constraints and so on. I won't go through each one of these examples, but these are things that you can do as well. You can adjust costs for individual generators. Anytime you're doing any of these things, just like we did with the change from area to super area control, I find that the difference flow tool is often really gives you a lot of insights in terms of, you can see a solution with one set of assumptions, change the assumptions around and see how does that affect the assumptions. So you might see, like, if a generator is out of service, how does that affect the expected LMP at a certain bus? Or if the generator is in service, how does that change things? So difference flows tools are good for that. Contouring is kind of good to see things like that as well. So the remainder of the slides are just kind of for information only, but just looking at other things you can do with the OPF. This first example, this is not one that we have as a hands-on example, but it was done, I think, for somebody's research at the university, a 30-bus test case where what was done is a generator at bus 13, assuming that generator can adjust its bids and also assuming that the rest of the system is static. The loads don't change, the other generator bids don't change. We just want to see where would this generator like to bid into the market in order to maximize its profit. And the assumption is that it has a fixed actual cost of $7 per megawatt hour, and then it can bid whatever it wants. So the profit function is determined by the LMP, the resulting LMP, times its output minus 7 times its output. So ideally, you want an LMP at your bus to be, greater than your true cost if you're a generator. And basically by varying the bid from the generator in 50-cent increments, a series of optimal power flows can be solved, and then you can determine where that function hits its maximum. Again, this just assumes that the rest of the network doesn't respond, and if the generator bids too much, then it doesn't get dispatched at all. So that's why the curve kind of falls back here. If it's bidding out here, then its output's going to be 0, and then it doesn't make any money. If it's bidding down here, then it influences, it exerts an influence over the local LMP, and it doesn't make as much. So, and then next there's just some graphics that are taken. We're going to do a large scale example tomorrow too, but same principles apply. It's kind of harder to see the moving parts when you fire up a large case though, but you can kind of zero in on those things with contouring, with difference flows and things like that. But this is a larger case in the Northeast from almost 20 years ago. Supply curve kind of looks like this. Demand, if we ignore transmission constraints and we assume that demand is fixed, the curve is vertical and comes here. So if we ignore transmission constraints, then you'd get a single LMP everywhere at this level. But of course, with transmission constraints, you get different LMPs. So that's the network. This shows the pie charts are dynamically sized so that if a line's at or exceeding a limit, it's large, so you can kind of see where the binding constraints are. You could also contour the shadow price for transmission lines, and that would kind of help those jump out as well, so you see where the binding constraints are. This is looking at a contour of the pricing, where the large range just means the range on the contour right there from 10 to 50. If that's narrowed up 32 to 40, then you can kind of see some more granularity and more differences in here. There's like a load pocket here and some other constraint along there that's causing different prices on different sides. If we look at individual areas, like if we split New England and New York, then you get a seam along there that's caused by enforcing, just like we saw in the 7-bus case. If the area with more expensive generation is not allowed to import more, then you can get high prices in one region and different prices in another. A generator, this bus 6642 is somewhere in this pocket. So if that generator is out of service, you get a load pocket here. It's kind of what we saw in the 3-bus case with the generator at bus 3 out of service. We can't produce any power locally. So we get unenforceable or binding constraints depending on how much load is at the bus. And if the generator is available, then it can do away with that load pocket. Even if it's a very small generator, you can still then, it's enough to provide marginal power within that pocket that you don't have when it's off.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular PowerWorld engineer, please feel free to contact that person directly.